We're going to look at objects that basically are in free fall, right? They're moving in the vertical direction with nothing attached to them, right? So anything that's considered free fall, anything that's freely falling through the air, is still considered to be at constant acceleration, right? We talked about how our kinematics equations don't work unless we have constant acceleration. So free falling is still considered a constant acceleration. Okay? It's still accelerating as it falls. Okay, and that has to do with you're right. No acceleration once it reaches terminal velocity. Very good. Very good, Griffin. Very good. Object.
Like when people drop pennies from the top of the Empire State Building, they can't kill people because it only goes like 40 miles an hour.
So it depends on how
People have been blinding me for years now.
What? You can't kill.
do heavier objects fall faster than light objects? What do we think?
I bet they're slower.
You think heavier objects fall slower than lighter objects?
No.
How many of you think heavier objects fall faster than lighter objects? How many of you think opposite, light falls faster than heavy? How many of you didn't vote? Most of you.
A rock is gonna go faster than a feather.
Okay, the answer is no. Heavier objects don't fall faster than lighter objects, but there's a little caveat. As long as they're shaped the same. Okay, as long as they're shaped the same. So, excluding air resistance, which we do in high school physics, right? We live in perfect physics world in high school physics. We're going to assume that two objects of the same shape are going to fall at the same rate, no matter what. Okay, I want you to look at your kinematics equations real quick. We're going to use these same set of equations for vertical objects. So do you see anywhere in your kinematics equations a term for mass? No. Which means mass doesn't have any effect on the rate at which things fall. Okay, so let's look at the case, right? We're going to watch a really historically accurate video here. 9.8. 9.8 meters per second squared. You know it's an acceleration because it's still measured in meters per second squared. Okay, so that means for every second that an object falls, its velocity increases by an amount of 9.8 meters per second.
Just put it on the sheet.
You can put it on there. You're going to use it so much you'll end up memorizing it, but you can put it on there. And realistically, I want you to put that as negative because what direction does gravity always pull?
Down.
Down. Okay, so I want you to put that as negative 9.8.
That's what I was thinking.
Okay, so I want you to include a negative because gravity, no matter which direction you throw the object, is always going to pull it down. Okay, so gravity always acts in the downward direction. So the good news is that for your kinematics equations, every time you see an A, and we're using vertical equations, and we're using vertical situations, A is always going to be negative 9.8. Always, no matter what. Okay? So for vertical problems, your acceleration is always negative 9.8 meters per second squared. Okay? Yeah, go ahead and you can put the negative there. The value for it itself is 9.8. I'm telling you, since it's always going to be going down, I want you to add that negative. Okay. All right. So whenever something is in free fall, it's considered to be free fall as soon as it's no longer attached to anything. Right? As soon as something flies through the air unattached, it's considered to be a freely falling object. Okay? So they have constant acceleration in the y direction. If I say y direction, does that mean horizontal or vertical? Vertical. The y-axis is vertical. The x-axis is horizontal. So we'll think about our variables in terms of y's and x's. Okay, so constant acceleration in the y direction is negative 9.8. Okay, that's all you need to know there. Okay? So whenever we talk about vertical kinematics, your acceleration is always, always, always negative 9.8. I'm going to say it over and over again because you still will forget. Okay, for vertical problems. All right, let's try one here. Okay, so drawing the diagram becomes extremely, extremely important when you're talking about vertical problems.
do you think are easier?
All right, so we know our here's our little tower. Here's a ball. It's going to get dropped, and it's going to fall downward. Okay, our tower is 70 meters high. That's as artistic as your drawing needs to be, okay? Because you will find that I have 0 artistic skills, okay? So that's it. So, can anyone tell me a variable that we have, or even just tell me what are we solving for? That might be the easiest one. Which one? Distance, right? We're solving for final distance. Because we want to know how far it has fallen, right? How far down has it fallen after 1 second, 2 seconds, and 3 seconds? Okay, so we're going to have 3 different answers here. This isn't a problem in which we can solve it just once and get 3 different answers, right? We have to solve it 3 times. So we want to find final distance. Where do we always put our origin at? We put it at the start of our motion, right? So the ball starts on top of the tower. This is where it becomes really important that you put the origin at the start of your motion. That way you know your initial displacement is 0. Okay, that's what we're saying. We know our initial displacement is 0 because we put the origin there instead of putting the origin at the ground. Okay, so it didn't have a lot of effect on you when I was saying that for horizontal problems. For vertical problems, it really does. Okay, it makes a difference where you put that origin. Okay. So, can someone give me any other variables that we know?
Acceleration.
Okay, we know acceleration, which is good. And Hallie, what was the other one you were telling me?
1 second for time.
Good. Time is 1 second. Okay, so we're only going to solve this part of it first. There's one other variable that we know that's given in context clues. Okay, if we say that it's dropped, what do you think that initial velocity is? 0. Yeah. Okay, so that means that the second I let go of it, that instant that I let go of it, it hasn't started moving yet, right? It's at 0 velocity. If I would throw the ball down, that would give it an initial velocity. But since I'm dropping it, that's a big clue that your initial velocity is 0.
So for every problem, will the acceleration be negative 9.8?
Anytime we're dealing with vertical motion, yes, always negative 9.8. Okay? So, do I need to know my final velocity? No. What equation can I use to solve for final displacement? The second one. Okay, so let's use the second one. All right, we didn't have to convert any of our numbers because we were given in seconds, meters per second, all that kind of stuff. Bless you. Good. What would our units here be for displacement final? Meters. Good. Okay, so that's our final distance or displacement. Why does it come out negative? Good. It's going down, and more specifically, it's ending up 4.9 meters below where it started. Okay, so for displacement, we think about here's where our origin is, right? Here's our coordinate system. We're ending up below where we started. So that's why it comes out negative. So anytime we have a negative displacement, that means we're below where we started or we're behind where we started. Okay, very good. So now for the second part, it says after 2 seconds, what's the only thing that has to change? Time. So we can use the exact same equation. We're just using t equals 2 seconds. Oops. Would we be expecting our displacement to just be doubled since our time is doubled? That square throws it off. Okay, so since it's not falling at constant velocity, we can't expect our displacement to just be doubled. The only thing that changes for the last one is time. Okay, do we agree? All right, so I want you to see on this diagram how after every second, the distance in which we have fallen has increased, right? The intervals between those have increased with every second. That's because of acceleration due to gravity, right? It's not falling at a constant rate, it's speeding up, right? It's speeding up as it falls. So the intervals between those time or those seconds should be getting greater, which it is. Okay, any questions here?
So if it's high enough to hit at one point, it would just be the same.
Mm-hmm, eventually. Yeah, we won't deal with that in calculating it.
So you can't.
We wouldn't calculate terminal velocity. Yep. Okay, so the ball from the last problem is now thrown instead of dropped. Right, it's still going to travel straight downward. We're still going to place our origin at the top or at where the motion starts from. But what would be a variable that would change here? Good, initial velocity. Okay, and what does our initial velocity become? Instead of being 0, because it was dropped, now it's being thrown downward. What should our initial velocity be? Positive 3 or negative 3? Negative 3, that's important, right? Because it says it's thrown downward, you have to know that it's going to be a negative. If it was being thrown upward, it would look something like this. Right here's our cliff. It would go up, and then it would come back down. Our equation would take that all into account, but that's not what we think the motion is doing, right? We just know that it's being thrown straight downward. So we have to make sure our velocity there is negative. Okay, our time is 2 seconds. What's our initial displacement? 0, right? Because we want to find how many meters it's fallen. And what are we solving for here? Distance final. Good. Okay, so again, what equation could we use? The second. All right, go ahead and plug that in. Would we be expecting our displacement to be farther down than when it was dropped at 2 seconds? Or closer to the top? Further down. No,
Jump on 2 balls.
only one. Isn't that just called tossing? So my little diagram here is the purple means it's on the way up, red means it's on the way down. Okay, that's all we're talking about. We're assuming this ball is going straight into the air and coming straight back down, not moving horizontally at all. Okay, so the first part we're going to look at is how high it goes. That's the first part. You can't solve both of these with the same equation because we want to find final displacement and we want to find time. We can't do that in the same equation, right? We can't solve for 2 variables. So the first thing we're going to look at is how high it goes. Okay, so Sammy, why don't you give me one of our variables here? Good. And is it positive 15 or negative 15? Positive. Good, because he's throwing it upward. Okay. What other variables do we know, Griffin?
The final velocity is 0.
Good. How do we know final velocity is 0?
Because the ball stopping for a second.
Good. Good, good. We're only concerned about the first half of the motion because we want to know on its way up, how high is it going to go? So at that highest point or at its peak height, you'll hear me say the term peak height a lot, it pauses for just a second before it falls again. Okay, so that means its final velocity at its peak height right here is 0. Very good. What other variables do we know?
Acceleration is positive 9.8.
Yep. No. It's still negative. Always negative no matter whether the ball's going up or down. That's tricky. Because gravity's always going to pull you down. Okay, so just think of it like that. Gravity's always pulling us down, so gravity's always going to be negative. Okay?
That's all we got.
That's all we got. What do we know about our initial displacement?
0.
0, right? Here's the origin, where our motion starts from. So di is always going to be 0. So what equation can we use to solve for final displacement?
Last one.
The third one, right? Because we don't have time yet. Okay, so the third one. Let's use that third one. I want everybody to be plugging this in. I want to make sure you can get them to come out right. Bless you. Okay, so algebraically from here, my next step is going to be subtract over that 225. And that leaves me with negative 19.6 times df. So how do I get rid of the 19.6? Do I add it over or do I divide it over? Divide it over. So my distance final is equal to 11.5 meters. Right, so he's really tossing that thing in the air. It's like 33 feet. So, does it make sense that our displacement comes out positive?
Yeah.
Yeah, because we're above where we started, right? So that's good. Okay, last part here is calculate how long it's in the air total. Okay, do we have any questions about how we found displacement? Okay, so let's look at time now. We want to know the total time. So there's a couple different ways we can do this. One of which involves the quadratic equation, one of which does not. This is what I call the shortcut method for solving for time. Okay, this is what I'll refer to as a shortcut method, whether it is or not, whatever. In this motion, on the way up, on the way up and on the way down, it should theoretically take the same amount of time to go up as it does to come down. Okay? It actually is, yes. It's really, that's really the case. Okay, because as it goes up, it's going to slow down, right? It's going fast, and it's going to slow down. On the way down, it's going to start slow, and then it's going to speed up. Okay, so it should take the exact amount of time to go up as it does to come down. Okay, which means, which in this case it is, right? It's starting and it's ending at the same height. This guy's hand, right? Our start and our end height are the same. So, essentially what we're going to do is solve for the time on the way up, and then we can just multiply it by 2. That's it. Right? That's the shortcut method. So if I want to solve for the time on the way up, what are some things I know about this first half of the trip? Okay, first half of the trip, I know initial velocity is 15. I know final velocity is 0. I know acceleration is negative 9.8. Right? That's enough for me to use the first equation to solve for time. Okay, but as long as I have final velocity equals 0, that means I'm only looking at the first half of my motion. Because final velocity would not be 0 at this point, right? It's only 0 at its peak height. Okay, so I'm going to solve for time. Time should never come out negative, so if you get a negative time, that means you did something wrong. Okay, I'm just telling you right now. We need to subtract over the 15 and then divide by negative 9.8, and that gives us time equals 1.53. Okay, is that where we stop? No, we have to multiply it by 2. Okay, because 1.53 is only the time it takes to reach peak height. We multiply it by 2 to get the total time. So that means total time for the trip is 3.06 seconds. So this method works anytime we have symmetric motion. Velocity and acceleration are not always in the same direction. So we saw this example, when we have a positive velocity, it does not mean that our acceleration is positive, right? Acceleration is always going to be negative 9.8. So our velocity and our acceleration don't have to be in the same direction. Our velocity can be positive, right? We're throwing something into the air, but our acceleration can still be negative. This is pulling us down. We're slowing down in the positive direction, which means our acceleration is negative. Okay, at an object's highest point, what's its velocity? 0. Okay, that's something that you got to know. At its peak height, or at its highest point, final velocity is 0. Okay. So that's something you need to remember or write down. What's my object's acceleration at that point? This is a little tricky, but what's my acceleration at our highest velocity? Or highest? Negative 9.8. Does gravity ever stop working? No. So no matter what your velocity is, your acceleration is always negative 9.8, which is tricky to think about. Okay? That's where we're going to stop with our kinematic.